Hey guys, welcome back to Computational Biology with Python. In this last section last section of this subject, we're going to finish up our Seq tutorial here. And so we ended with unknown sequences in the last one, so we'll kind of continue on that path here and finish it out. Okay, so at the end of the last one, we had these undefined sequences, but we knew the length. So sometimes you can get, for an example, this is so tiny, view, zoom, view, zoom. Zoom in so you can see. Okay, so sometimes this is like a sequence alignment printout. So here we have macaque and human and mouse and some other animals that we're comparing these sequences. And so what this information gives us here is we have the start position on the chromosome, the length of the sequence, 36, and the length of the overall chromosome, and then the sequence that we're comparing. And so sometimes we don't know all the letters though beyond that. We'll save this up here. So we can pull some of this stuff. So let's do, where's my note? All right. Seq 1175126883. And then we'll do TTGAAAA, CCTGAA, TGTGA, GAGTCAG, TCAA, GGATAGT. All right, I hope that's right. And then length equals 159345973. So this is just, so what we did here is we just pulled the first one from this file. So this is just the human chromosome one. That's what that is. Okay, now what we can do is say Seq, give us 1000 through 1020. And so it says we have none. We have a length of 20, but we don't know what those 20 are because they're not defined in our sequence. We could do Seq 1175126990 through 11751268. Wait. No, 12700. Okay, so if you do this, those are defined, right? Because we started at 83, so we're just 7 base pairs into here, right? So we have CCTGAA, so CCTGAA. So this is where it starts because that area is defined. Previously, the first 1000 we don't have defined because that's way upstream over this way. What else can we do here? Let's do Seq Seq 1175126870 through the end. And so it'll give us everything that we know, and then the length of the total amount of that Seq object, which is just through the end of the chromosome, it appears. So yeah, so you can this just shows that you can have partial information of a chromosome combined with unknown information and like placeholders for length. So you can also create these partially defined sequences by appending, just like we appended previously. So seek equals seek ACGT, and then we can say undefined seek equals seek none. So we have no letters where nucleotide's known, but we know that it's 10 base pairs long. And then we can do seek plus undefined seek plus plus seek. Okay, so we are putting this at the beginning and the end, and then we have our 10 base pairs that we don't know in the middle. So this is what we get. So the length is 18. We start at 0. We're with ACGT, and then we go through 14 because we have 10 in between. So we have 4 plus the 10, and then we end with ACGT. So just like the normal a normal Python string as opposed to a seek object, the object is read-only. So we call this immutable in Python. So this is useful since in many biological applications you want to ensure that you are not changing your sequence data, right? So let's do my seek equals seek GCCATTGGAATGGGCCGCTGAA. So let's run that. So now let's see what happens when we try to edit the sequence. So mySeq. So this is like if you took R or the intro Python, you could edit a number in a sequence. So we're going to say, okay, the 5th position in this sequence is going to be G now, because it currently is T. If we do this, doesn't like it. And so this is on purpose because you don't want to be inducing fake mutations into your sequence, right? Accidentally throughout your code. So it's immutable, so it means it's not able to be changed like that. So let's get rid of this so we don't have the error here. But I just wanted to show you that. But you can create a mutable sequence. So Bioseq import mutable seq. So if you want to from Bioseq, not just Bioseq, from Bioseq import mutable seq. So if you wanted to do some sort of experiment with randomly mutating genes or something like that, you can create a mutable seq. So mutable seq equals mutable seq for mySeq. But this isn't available by default, so you have to import this mutable seq thing because it's kind of protecting you in a way. So mutable seq. So you see we have our mutable seq from before. Now if we wanted to do mutable seq the 5th position, 5 equals, we'll change it to a C. And now we will print mutable seq again. Mutable seq, there we go. Now you can see the 5th position is now a C instead of a T, because we are able to do that. And so we can also do things like this. I don't know what the point of this would be, but mutable seq, lowercase, we can do remove all the T's, and then if we do mutable seq, you can see our sequences. Oh wait, what's going on here? Let's see. Oh, so it just removes the first T, which is interesting. Like I said, I've never used this command. I don't know what you would use. Maybe you'd find some use for it, but yeah. Anyways, so you can also do, just like with regular sequence objects, you can do mutable seek reverse. You get the reverse up here. Oops. Oh yeah, and then we have to call it again. So you get the reverse of your sequence. So yeah. What else do we want to do here to finish out? Oh, so what if we want, after we've like changed, so if you wanted to like change your code or change your gene and then get back to protection of making it immutable, you can do something like new seek equals seek mutable seek. So now your new sequence, if we print that, you can see it's just a seek and not a mutable seek. So now it's back to being protected from being able to change anything in it. Let's see. So if for some reason you really don't want to use the seek objects, which I don't know why you would do that, we can, it's just much easier, but there are, in case something comes up, let's do this. Import, reverse, complement, transcribe, back, transcribe, translate. So let's import these packages here. So you can do like a string, my string equals gctg gtatggg tcgtt ggaa gggt ggt cgt gct gct gg ttag. You can put whatever you want. I'm just doing what my notes have. We do reverse complement my string. So these packages, or these functions here that we imported, just work on strings as opposed to like the built-in dot when you put the dot before the function name. So say you don't want to install Biopython for some reason, you're working on a computer that has no room for it or something like that. You need to transcribe it, back transcribe my string, and then what was the last one? Oh, translate. And translate my string. And we got our stop code on. Nice. But I would work with the seek objects. It's just easier because you don't have to load all these packages. Everything's already built in, so you had to load a single, or all these functions, so I had to load like a single function for each command. But if I just load the seek package, or the normal seek, like up here, import seek, then all that stuff's included. So, all right, I'm gonna save this to my files. That is it for seek objects. To it, you want to look at a codon table or the differences in transcription between nuclear and mitochondrial genomes. If you want to translate it and transcribe it, all these different things the seek package is built for. So when you're focusing on kind of molecular stuff, say you're looking at like a cancer gene, or a gene that you think might be responsible for cancer, and you want to kind of characterize it genetically, seek objects in Biopython are awesome for that. All right, that's it for this video. If you're watching on YouTube, please hit like, please hit subscribe. And thank you for watching, and I will catch you in the next video.